So, in the last lecture we have read the read how to frame the recurrence relation, and today we will see how what are the different techniques to solve the recurrence relations. And already we know that solving recurrence relation means to get an explicit formula. That means, if the nth term of the sequence that is related to the predecessors, that means it gives then how it is related to n only, that is the explicit formula. So, the solving recurrence relations, what are the different techniques we used? So, first we see very simple type of recurrence relation. We will use first the iteration. First we will see that how we can use iteration to solve the thing. Second, we will see that how to solve the linear homogeneous recurrence relation with constant coefficient. Okay. So, first we see the how we can apply the iteration to solve recurrence relations. Okay. So, we take one very simple examples of sequence. Say I have a recurrence relation with n minus n equal to n minus 1 plus 3, and I give that a1 equal to, initial condition is a1 equal to 2. What is iteration? That I can again replace n minus 1 by n minus 2 plus 3. So, I get n minus 2 plus 2 into 3. Again I can replace n minus 2 by n minus 3 plus 3, and so this becomes 3 into 3. So, in this way, if I continue, I can write n minus 4 plus 4 into 3, and if I continue, I will be getting a n minus 1 plus n minus 1 into 3. This is a1 plus 3 n minus 1. Now, I know a1 equal to 2. So, this becomes 2 plus 3 into n minus 1. Now, see, we started with a recurrence relation. This is my recurrence relation, given a simple recurrence relation I have taken. This is my recurrence relation, and if I just iteratively we proceed, we replace each term by its predecessors, the relation we apply, I will get the relation that here n depends on the predecessors n minus 1, here n depends, here I get the n is, here I get n equal to 2 plus 3 into n minus 1. So, this is my explicit formula or the solution. This is my solution of the recurrence relation, because it depends only on n, or I can tell this is explicit formula. Now, already we have read one example of the number of subsets of a set. If we remember that the example that we have given, the if Sn be the number of subsets of an n element set, then we have framed the recurrence relation like Sn equal to 2 Sn minus 1 to Sn minus 1. Now, if I apply iteration, so this is my recurrence relation, again this is my recurrence relation. Now, if I apply iteration, so this becomes 2 Sn minus 2 to Sn minus 2, which is 2 square Sn minus 2. Again I can apply 2 square into 2 Sn minus 3, so this becomes 2 cube Sn minus 3. In this way I can apply, this is 2 to the power n Sn minus n equal to 2 to the power n S0, which is 2 to the power n into 1, because for one element S0 means empty set, this is only one subset, the set itself. So, I gave that I get that Sn equal, the solution is the Sn equal to 2 to the power n. So, this is my solution and we apply iteration. So, apply the method of iteration. Now, this Sn equal to 2 to the power n, this solution we get when my recurrence relation is Sn equal to 2 Sn minus 1. So, this is a very important thing or very primitive solution that we will be applying, or we will be using this solution when we will use or we will try to solve by a linear homogeneous equations. So, we remember, we must remember this solution, we must remember this Sn equal to 2 to the power n and the recurrence relation is Sn equal to 2 Sn minus 1, we remember. Now, we will give the solution technique for solving linear homogeneous equation with constant coefficient. So, first we define the linear, we give the definition of linear homogeneous recurrence relation of order k. Okay. So, a linear homogeneous with constant coefficients. Is an equation of the form of the following form. I write that n equal to C1 n minus 1, C2 n minus 2 plus C3 n minus 3 plus Ck n minus k, where Ck not equal to 0 because it is of equation with order k, and here the k initial conditions, we need the k initial conditions as if A0 equal to C0, A1 equal to C1, then Ak equal to Ck. And here this small C0 C1, okay, I give the A0 equal to C0 dash, otherwise both are C0 C1 Ck. So, these are my k initial conditions, and these C1, C2, Ck are constant k number of k constant coefficients. So, we define that linear homogeneous recurrence relations like that. Now, already we have seen that Sn equal to 2 Sn minus 1. This is a recurrence relation, and I tell that this is a recurrence relation of order 1. And this is a linear homogeneous recurrence relation. Or the Fibonacci sequence, Fn equal to Fn minus 1 plus Fn minus 2. Here the constant coefficient is 2. 2 is the constant coefficient. So, as if we can write 1 Fn minus 1 plus 1 Fn minus 2. So, here this is a linear homogeneous recurrence relation of order 2, and 1 is the coefficient, constant coefficients are 1 1 are the constant coefficients. It is linear since the power is 1. Okay. Now, if I write n equal to 3 n minus 1 n minus 2, say into. So, this is not a linear homogeneous recurrence relation. Or if I write n minus n minus 1 equal to 2n. So, this is not a recurrence relation, not a recurrence relation, since there is no relation here that where the nth term depends on the predecessor like that. Or if I write n is say 4n n minus 2. Again this is a recurrence relation, but not with constant coefficient, because here coefficients are 4n is not a constant. So, it is a recurrence relation, it is a recurrence relation with not constant coefficient, not constant coefficient. So, now it is clear that normally with linear homogeneous equation with constant coefficient, what do we understand? Now, we take an example that for solving linear homogeneous relation. So, we take an example for solving. So, solve n equal to 5 n minus 1 minus 6 n minus 2. Initial conditions given are a0 equal to 7 and a1 equal to 16. Okay. So, we see the solution. So, first thing, this is a linear recurrence relation, homogeneous with constant coefficients, 5 and 6 are constants. So, now let the solution is of the form say Vn equal to t to the power n. So, if we remember that recurrence relation of Sn equal to 2Sn minus 1, we got the solution that Sn equal to 2 to the power n. See, this simple form that we are using here, since here it is of order 1 and it is a linear homogeneous recurrence relation of order 2. Now, the solution we have taken as if the of the form is t to the power n. Okay. So, this is the technique normally we use to solve the linear homogeneous recurrence relation. So, Vn is t to the power n. Since for the first order solution first order solution, we get solution, we have Sn equal to 2 to the power n, as I mentioned, for the recurrence relation, Sn equal to 2s n minus 1. So, we have taken this form. So, now if I put here, then I get Vn is 5 Vn minus 1 minus 6 Vn minus 2. I put the solution, since Vn equal to t to the power n, this is the form. So, this is my form, t to the power n equal to 5 t to the power n minus 1 minus 6 t to the power n minus 2. So, I get t square equal to 5t minus 6. If I divide the both side by t to the power n minus 2. So, I get the equation t square minus 5t plus 6 equal to 0. So, I get t minus 2 into t minus 3 equal to 0. I get t equal to 2 and t equal to or t equal to 3. I get two solutions, that t equal to 2 and t equal to 3. So, we have two solutions here. Set S and T. So, I can write Sn equal to, when t equal to 2, 2 to the power n, that is t equal to 2, and Tn equal to, we get 3 to the power n, that means t equal to 3. So, our general solution, that the general solution form is I get the Bs plus dt. So, I can write the solution Un equal to Bsn plus dTn, and we remember the initial conditions are A0 equal to 7 and A1 equal to 16. Now, we have to find out the constants B and D. So, we continue, this is continued. So, we put the initial conditions. The initial conditions are, so again if we just write Un equal to B 2 to the power n plus D 3 to the power n, and A0 equal to 7 and A1 equal to 16. So, we put the values. So, 7 equal to B 2 to the power 0 plus D 3 to the power 0, that means B plus D equal to 7. And 16 equal to b 2 to the power 1 plus d 3 to the power 1 or 2b plus 3d equal to 16. Now we can solve. If we solve and we solve, so solving equation 1 and 2, we get b equal to 5 and d equal to 2. So, we get that un equal to 5 2 to the power n plus 2 3 to the power n. That means my solution is I have taken n. So, n is 5 2 to the power n plus 2 3 to the power n. So, I get an explicit formula or the solution of an. So, this is my solution of the recurrence relation. We have taken the recurrence relation. If we see that n 5n minus 1 minus 6n minus 2, solution of that n equal to 5n minus 1 minus 6n minus 2. So, this is the solution technique of solving the linear homogeneous relation. Now, we have given the techniques. Actually we can write the same techniques in a form of a theorem. So, I give the if I state the theorem that I can write the statements for second order. Okay. Okay. So, this be a second order linear homogeneous recurrence relation with constant coefficient. Now, if S and T are two solutions, then we get then U equal to Bs plus dt, and B and D are constant coefficients. Now, solution of recurrence relation we get, this gives the is this also a solution of recurrence relation. Now, if R is a root of t square minus C1t minus C2 equal to 0, since we have considered a second order recurrence relation, then the sequence r to the power n for n equal to 0, 1, 2 is a solution so if A is the sequence defined by A0 equal to C0, A1 equal to C1 and R1, R2 are the roots with R1 not equal to R2, two roots are different. Then there exists B and D. Earlier we have taken that Bs plus dt, that n equal to B R1 to the power n plus D R2 to the power n equal to 0, 1, 2 as the solution, is the solution of the second order equation. So, the example I have taken and the theorem statement is if we follow the example, the theorem statement is written as if this is the procedure or the technique that we follow to solve the linear homogeneous recurrence relation. So, this is stated in a theorem and the same thing we have explained with an example. So, next lecture we will see the other techniques of solving recurrence relations.